Good afternoon, everyone. The diversity theme should have continued because my PhD student should have presented this. She's in Glasgow, so I'll fill in. Even the color pattern is selected by her, so it reflects. So I would present, and it's very in keeping with the theme of the previous two talks. So it's a type of electrolyte gated transistor sensor technology that I would like to share with you. Along the evolution path that it has taken so far, and it's targeted towards saliva sensing. In this specific example, we are demonstrating it for cortisol. So I wanted to share a couple of slides here about the evolution of point of care and variables, and this is based on an excellent review paper in Nature Biotechnology, which kind of talks about how the ambition of academic researchers and the demands of the industrial sector has grown over the last couple of decades for wearable and point of care biochemical detectors, moving from simple lab on a chip system. Simple lab on a chip type platforms where the demand was only for like sample handling, etc., to more sophisticated scenarios where the lab on a chip now is integrated with electronics, at least electrodes. And then there's a separate reader sort of arrangement. So the Abbott iStat, the Siemens Epoch analyzers fit in this module, and this is current. But there's an emerging wave of sensors, either wearable or portable, which is kind of looking to combine not just the fluidics, but also the electronics, hopefully either on a single platform or a small component where the reader is portable and can be just based on proximity interact with the sensor. And obviously the proposed or the futuristic, as you see, movies like Minority Report. I'm a little dated in that movie department, but implantable. So, you know, where you basically have implants in the body and they monitor your physiological signals, etc. So the challenge is not just the technology, the challenge is also the biofluids that will enable those frontier work in this generation and the generations to come. So obviously the current, the iStat, Epoch type of systems are blood-based, very dynamic, very well established, but if you move towards wearable, sure, the glucose monitoring is still blood-based, but a lot of ambition is to move away from blood-based detection for obvious reasons, the risk of contamination, the requirement of a phlebotomist, so it has to be somewhat clinical sample collection, and the sample shelf life. So even the Abbott iStat and the other technologies from start, as soon as you do the calibration, you only have like 10, 20, 30 minutes to complete the assay. Otherwise, it's a waste. The entire sensor chip is a waste. So alternative solutions that are non-invasive or minimally invasive are dermal interstitial fluid, so skin patch-based, sweat-based detectors. Tear fluid is an excellent candidate. Exhale breath condensates along with the exhale breath for volatile analytes as well as small molecules. And saliva continues to be a really promising non-invasive biofluid sample. The advantages, of course, are the ease of access, the lower risk of contamination, and that it can be handled in less biohazard certified settings with minimal certification, relatively less certification required, I should say. The disadvantage, of course, is that based on the transport phenomena from the blood capillary to these non-invasive fluids, there's an obvious order of magnitude drop in the analyte concentration. So that's a challenge. So these sensors have to be much, much more sensitive than your typical blood-based sensors. The other challenge is the larger variability. So blood, although it varies in terms of its analyte composition, the variation is not as fast. Whereas in saliva, if I had a coffee, my analyte levels will be like off the chart on so many different targets. Or while I'm, giving a sample, if I have like a micro injury during the sample collection, that will open some capillaries and the concentration of some analytes will just balloon. So those challenges remain and need to be addressed. For this work, at least, we relied on passive rule, which is a really tedious process. Thankfully, the students volunteered for it. I didn't have to, but it took them like half an hour to an hour to collect samples while avoiding micro injuries. But it's possible. We are looking into integrating that in our current clinical trial effort. So we chose saliva, and most of the targets that we have worked on with this technology has been hormones. Those hormones are amazing. The free hormone hypothesis allows a nice correlation between blood and saliva, and they're excellent for continuous health monitoring as well as for periodic checkups sort of application. So this is the domain we wanted to look into. Obviously, it's expandable to other kind of infectious disease, for example, and other domains. But we focused on hormones based on this hypothesis. And again, the active and passive diffusion allows us access to not just small molecule hormones, but also to large proteins, antibodies, etc. in saliva. So the footprint itself. So most of us are aware of the glucose, the variable glucose sensor, the EPOC blood gas analyzer, the aptasensor. There are almost approved, maybe not for clinical diagnostics, but there are tests for saliva, for example, for HIV, at-home HIV tests, and then there are emerging technologies that rely on OECTs and electrochemical detection for monitoring analytes such as uric acid in saliva. So there's definitely a lot of activity. I could have made this into like a mosaic. There's so much activity, but I just wanted to give a couple of examples here. Okay, so my life is easier now because we have already covered OECT, EGFET, and this morning the talk was all about different kinds of semiconductors, their tunability. So generally speaking, there are many different configurations in which a biofluid or an electrolyte can be integrated in a transistor architecture. The EGFET was just described by the previous presenter. And then there are OECT configured as ion selective FETs. There is an extended gate FET, which is essentially kind of separates out the electrolyte from direct interaction in the stack, but uses the 3 electrode assembly to then have the same kind of sensing response. The technology that we have been evolving for the last 3-4 years, we call it OEGFET. It's a little bit different than all 3 of them because the electrolyte is not directly in contact with either the gate or the semiconductor. We chose to do so, and I'll try to explain a little bit about it, because we wanted to have the ability to create a biofunctional layer, which can be tuned for specific bioassets. Most of the sensors that we have demonstrated in these configurations have been aptasensors. So aptamers are just as stable, perhaps more stable than antibody type of biomolecules. So we like the idea of immobilizing them. They give us extended shelf life, and they can be patterned very easily on a variety of polymers using one-step functionalization. So that dielectric essentially is a biofunctional layer. And the bottom dielectric could be a self-assembled monolayer, or it could be a porous layer, just allowing minimal interaction to the semiconductor. So our hypothesis was that this will extend the shelf life for continuous health monitoring, because we didn't want it to be essentially disposable for all types of applications. So as you can see, we have gradually moved from rigid assembly to soft Carleton and glass top, that was generation 2, to Carleton, but the fluidics integration wasn't there. But more recently, within a year and a half, we have done a seamless assembly of soft fluidics. And I'll talk a little bit about that here. So we are not using conjugated polymers, although we are looking into a lot of candidates right now for obvious advantages, as it has been pointed out. We have stuck with trypspentasine, which is a modified small molecule conjugated P-type semiconductor, because it has really good surface variability, and we can tell because we have switched so many substrates along the way. So it's easy surface activation using UV ozone or an oxygen plasma, and then you get good variability. It also doesn't require very high temperature for annealing. It is only semi-crystalline, so there is variability to grain boundaries in batch-to-batch fabrication, which is one of the limitations that we have, and we're looking to kind of expand into improving it with a self-assembled monomer that provides a better stability. In terms of the dielectric stack, we have PDMS, a very thin layer of PDMS for interfacing with the microfluidics. We're using PVA because we have been constantly trying to cross-link into high K stable thin layers. PVSVQ is something that we have looked at, and we are also looking at more biodegradable type cross-linking. So we're looking at PVA carrageenan, which is sort of like a polysaccharide, but it cross-links really well and gives high K stable polymer layers, which can be deposited in really thin films. So we have stuck with PVA. We are constantly modifying and improving it, and the trypspentasine creating the channel of the organic electrolyte transistor. In terms of the modular assembly, this is fully flexible. So the top surface is capped on with inkjet printed metal. The microfluidic channel itself is a PDMS-based microfluidic channel, which is 3D printed. And the bottom surface is capped on. We have done liftoff so far. Inkjet printing hasn't given us the kind of resolution we want. We have started investigating aerosol jet printer, which looks like it will be able to give us the resolution. But we can also do the screen printing approach because our dimensions are not as fine. It's close to 40 micron in terms of channel dimensions. And the immobilization of aptamer is a one-step process. So it's a chemical modification of PMMA, which is a thin layer that we UV activate, and then we just expose it to aptamer solution in water, deionized water, and we incubate for about 10 minutes. So as the previous presenter said, incubation is a critical step, and aptamers being small molecule, as long as the surface is not heavily charged and clean, the interaction is pretty good, and we get stable assemblies, which is good for months if stored under a refrigerator, months, room temperature, month, close to a month. So that's where we are. The annealing steps, we have tried to be close to room temperature, like the PDMS curing is tediously long, but it doesn't require any temperature. And that's the Aptas process for linking the microfluidic channel to the bottom surface. We still do a little bit of baking for the PMMA just to get the rigidity once the aptamer has been immobilized. But the aptamer limits the temperature exposure that we can do, which is why the readout part is where most of our current deliverables are focused on. So the first step demonstration we have done is using a system on board configuration, where we have used the generic printed board design. We've gone for a minimum power requirement, USB powered setup, a similar kind of microcontroller, USB interface, a shunt to convert the amperometric sensor readout to voltmetric signals, and then additional EIS circuitry for calibration, because it's just amazing to have that as a control. So I'll quickly show you some results. The sensor itself has been demonstrated in previous publications. We have improved to lower the voltage requirements. So if you are taking a small zone, constant voltage readouts, you can see that it behaves really well as an electrolyte gated transistor. We see the modulation of both the current and the capacitance, which is expected because it is an electrolyte gated system. And the samples that are tested here are spiked saliva samples. So the supernatant was collected through passive drool, and then essentially analytes were added in various concentrations. The shelf life under uses, so day 1, day 2, day 3 of the same chip, is only up to a few weeks right now, and we certainly hope to improve that. If you're going to go the continuous health monitoring way, it has to be a few months at least. We also see the predictable temperature drift, but we haven't done the full calibration yet. And the system on board analysis shows the amperometric response to concentration differences. We have tested the calibration, it works well. The disadvantage is when we go to system on board, because of the interfacing we have, which is a combination of silver paste, inkjet printed, and a copper electrode providing some cladding, environmental protection. It's not as great. The contact resistivity hurts us, so we are only 10% of the desired current when we do system on board reading, but we do have the resolution and the sensitivity. So we are hopeful that if we improve the interfacing, and if we can improve the electronics from board to perhaps seamless hybrid flexible, we would be able to reach to the same levels of resolution sensitivity that we were before when we were doing with the parameter analyzer. So to conclude, I've demonstrated a fully flexible OEGFET with integrated soft fluidic sample handling, which has been extended to multiplex aptasensor design. The variability is minimal as long as the deposition step is consistent. Interfacing is to a system on board right now. We are incorporating onboard calibration and hoping to go towards hybrid flexible miniaturization. Extending the shelf life is in works, and implementing it for future targets. Our current work is looking at alpha-synuclein for Parkinson's detection. So a little more high impact perhaps than continuous monitoring, of course. So I'd like to thank the funding partners and collaborators and research staff, students, Roslyn, the PhD candidate that did bulk of the OEGFET work, and Bruno, a master's student that has since completed, which was more involved on the system on board. Thank you.